So today we'll be dealing with the thermal physics. So some of the questions regarding the thermal physics in this one, which consisting of the thermal expansions, heat transfers, and the other conditions, please. Okay, so except from the thermodynamics, so we'll be seeing in the other part. So today we'll be seeing the heat transfers and the thermal expansions in this case, please. So coming to the today's first question. The figure shows a glass tube is there. Coefficient of the linear expansion he has given it as an alpha completely filled with the liquid of the volume. Expansion is going to be the gamma. So he has given the coefficient of volume expansion of the liquid. That is the real expansion. Heating. On heating, the length of the liquid column is not changing. So he is asking now the relation between the gamma and the alpha. Okay, so what is going to happen here? Volume expansion. So liquid is being only the volume expansion here. So coming to the volume expansion of the liquid conditions, the volume is going to be the V is equal to volume expansion is equal to initial volume into 1 plus gamma into delta T. So this is the volume expansion of the container. But we can say that volume can be written as an area into length. Since its length is not changing, what can be changed in the area? The area after rising the temperature, this is I'm writing. After rising the temperature, I'm taking this one into account. So that means the area is going to be the change in the area can be written as an initial area into. This is going to be the 1 plus beta into change rise in the temperature into length. That is initial length. Since length is not changing, so you can write it as an it's going to be the L naught only initial length. So when I take this area A naught into length L naught into 1 plus beta can be written as a 2 alpha into delta T. So this is volume after rise in temperature is equal to the V naught, that is the initial volume into 1 plus 2 alpha into delta T. So now if I consider this as an equation 1 and this as an equation 2, equating 1 and the 2, we can cancel the common terms and I can show that the gamma is equal to 2 alpha. So this is our relation for the first condition, sir. So next phase, two rods are there of the same length. Okay. So length is same. L1 is equal to L2 is equal to, I'm taking it as a length is L. Now the material transfer a given amount of the heat in 12 seconds. So it is the material is taking to transfer the heat in 12 seconds here. Now when they are joined end to end, that means you are making the two rods into a series combination like this. So when they are joined in an end to end like this, that means in the series combination, it is taking a time of 12 seconds. So let me write it as a TS. But when they are joined along its length, that means parallel. So when they are being joined in the parallel condition, so this is your first rod and this is your second rod, which are being placed side by side. Since their length is same, so now it is taking, he is going to ask you, so what is the time of transfer of the heat in the same conditions? So all of them are going to be the same conditions. He is asking in parallel how much time it's going to take to say transfer the same amount of the heat. So now coming to the relation, thermal resistance is equal to so thermal resistance can be written as a that is R is equal to L by this is Ka, where K is called as a coefficient of thermal conductivity. Coefficient of thermal conductivity. Okay, so this is the one here as well. So from this relationship, we can say that is the thermal resistance R is inversely proportional to the remaining all other things are the constant, so it will be proportional to the K. So that means we can write it as an thermal resistance R1 by R2 is equal to K1 by K2. Now coming to the heat transfer, so we can write it as an heat transfer. So coming to the heat transfer conditions, dq by dt can be written as a, this is Ka into delta theta, that is the rising temperature, by L, or the same thing I can write it as in delta theta by thermal resistance. So from this one, remaining all other quantities are same. That means time is proportional to the, from this one, T is proportional to the thermal resistance here. Since T is proportional to the thermal resistance, so we can say that T1 by T2 will be equal to the R1 by R2, and that should be equal to your. So since it is inverse relation, I have written here wrongly. So it should be the K2 by K1, or else I'll put it as an K in the parallel by K in the series. So it's the same thing I'll be writing here. K in the parallel by thermal conductivity in the series conditions. So in this case, K in the parallel, that is if for the parallel case, for the parallel thermal conductivity is equal to K1 plus K2. Since both of them are the same, you can write it as a 2K. So K in the series, we can write it as an, since both of them are same, it's K by 2. So it will be the 2K by, it is K by 2. So that means T1 is 12 seconds by T2 is equal to, we can write it as an, so K in the series is K by 2. So T1 is the time for the first case where in the series conditions. Okay, so now, so if I put it in the reverse case here, this is R1 by R2 is equal to R1. We are taking it as an initial case, series conditions, and these things, please. So now K2, if I go for this one, so we can substitute the values. So that comes out to be the, so 1 by K, 1 by 4 conditions, or we can go for T2 is equal to, this is 48 seconds. So now we can go for here, this is 48 seconds. Coming to the next questions, in a steady state condition, thermal conduction, 1 second here. So, okay, so I think so. This should be equal to the 4, sorry. So this is going to be the 3. So your final answer T2 should be equal to the 3 seconds. So your answer should be here 3 seconds. Sorry. So next one, in the steady state the thermal conduction. In the steady state conduction, the temperature at the ends of the rods has been given as the 20 centimeters a long rod and 100 degrees and 0 degrees. Suppose if I consider this as a rod, the ends of the rods are being maintained at, suppose this is end A and this is end B. This is maintained at the 100 degrees centigrade and this is maintained at the 0 degrees centigrade. So this is a situation. So in this case, the total length of the rod is 20 centimeters. Now he is asking the temperature at a distance of some 6 centimeters from here. So let me name this particular point as a C. Since it is in the series combination, that is the rate of heat flow under steady state also dq by dt towards the total length A, the rate of flow towards the total length should be equal to the dq by dt along the length called as an AC. Now substitute the values. This is K area. Change in temperature for the A to B can be written as a, it is 100 degrees and 0 degrees. So 100 minus 0 by The length is 20 centimeters here, and the corresponding thing can be written as n. So this will be the K, and the area is going to be the A, and this is going to be the temperature change between the A and C is 100 minus, let me name it as a TC. By the distance is 6 centimeters, these are your common terms, you can remove this here. So this goes for 10 times, and this is 3 times, so this can be written as an 300 is equal to 1000 minus TC into 10. So this can be written as an 10 TC, that is the temperature at the sea, is equal to 700. That means temperature at the sea will be 70 degrees centigrade. So this should be your option, please. So next one, please, in this case. Next case, question number 4. A liquid having coefficient of volume expansion gamma naught is filled with mm, filled with a cylindrical glass vessel. Glass has a coefficient of linear expansion of alpha. So the liquid along with the container is heated. So liquid and the container, both of them are being heated. Fine. The mass is the container is going to be the negligible. So he has given certain options here. Center of mass of the system does not change. That means, for example, if I fill a container like this, and this container is filled with the liquid. Suppose the center of mass is located, imagine center of mass is located at this particular point. So after rising the temperature also, if the center of mass is not changing, after rising the temperature also, if the center of mass is not changing, the meaning of that one is the level of the liquid is maintaining the same after rising the temperature also. So this can happen only in one possibility, that is if expansion of container is equal to expansion of liquid. That means change in volume of the container is equal to change in volume of the liquid thing, please. So what is the change in the volume of the container here? It can be written as an volume of the container or volume of the vessel into gamma of the container if I take it. So initial volumes, whatever are there, they are going to be the same. So into change in temperature is equal to. So this is the volume of the liquid and the gamma of the liquid, that is the real expansion it will be, and this is delta T. So since these two are the same thing, volumes, so temperature rise is also same. That means gamma of the container can be written as 3 into alpha of the glass or alpha of the container into real expansion. So this should be the condition for the first case if center of mass is not going to change. So we can go for the option B. And similarly, the fraction in the C and D, if we come down, in the C and D, if the fraction of the volume of the container occupied by the liquid does not change due to heating. That means the same issue. So if this volume is not going to change on heating, then also it will be the same situation. So then also it will be the gamma naught is equal to 3 into gamma G. So it will be the answers is a multiple questions. B and C are your answers for this question. Next case, please. Next in this case, coming to the temperature of an isotropic cubical solid of length L naught and density rho naught, coefficient of the linear expansion is alpha, is increased by 20 degrees centigrade. Then at higher temperature, what will happen? It's going to be this. So what will happen at the higher temperature? So when you are rising the temperature, obviously the length of the is going to change. So or else L2 is equal to initial length into 1 plus alpha into, you can write general formula, I'm writing T2 minus T1. So now the rise in temperature, the condition that is L2 is equal to initial value L naught into 1 plus alpha into temperature is increased by 20 degrees. So it will be the 20 into alpha. So this is concerned to the option A. Fine. Now he is asking for the total surface area. So how can you write the total surface area formula? General formula of the total surface area, that is A2 is equal to A1 into or A naught into, this will be the 1 plus beta into delta T. So this can be written as an beta, can also be written as an 2 alpha, and area of the, since it's an cubical solid, area can be written as an directly area or A naught is equal to L naught square. We can write in this way. So next case, substituting this one. So L naught square into beta can be written as an, it is 2 alpha into T. So this can be written as an, so second option is also true. So this is concerned to the option B. Next one, sir. The density of, so coming to the density of the liquid. So density at a given temperature is equal to density at 0 degrees by, this is 1 plus real expansion or gamma into delta T for the solids. So gamma can be written as a density rho naught into, this is 1 plus gamma can be written as an 3 alpha into delta T. So this should symbolize this, let's compare rho naught into 1 plus. So since it's a 3 alpha, we can write it as an, so this is equal to the, uh, that is rho naught into, this is 1 plus 60 into delta T, and this can also be written as an L naught square into 1 plus, this is 40 into alpha. Closing this one, this is going to be the 60 into alpha. So this should be our relationship over here, 60 into alpha, option B. So these three cases are going to be the true cases. Now, next question, a body of area he has given. Okay, let's go for this one. So area is equal to 0.8 into 10 to the power of minus 2 meters square he has given, and the mass m is equal to 5 into 10 to the power of minus 4 kgs. This is the information given. So directly faces the sun, it is facing the directly sun. That means the radiation from the sun is falling on the body. The emissivity of the body is being given by, that is small e is equal to 0.8. And he has also given the specific heat. Let me take it as some C. Or yes, C, let me take it. C is equal to 0.8 calorie per kg. So we can come into, if I multiply with the calories 4.2, then it will be the joule per kg Kelvin SI units. We have converted this one. So the surrounding temperatures of this can be, that is small t, he has given it as in the degree centigrade. Let's try to convert in the Kelvin, that is T is equal to T plus 273, which is equal to the 300 Kelvin. So now he has also given the solar constant. S is equal to 1.4 kilowatt per meter square. Solar constant is sort of an intensity conditions. Okay, so this particular thing is going to be working on the Stefan's law. That is dq by dt, energy radiated per unit time, that is the power is equal to sigma EA T power 4. So from this one, this can be written as a mass into specific heat into D capital T by this one. So this is the value of our dq by dt. So let's have written the information for us. So now, when sun is been falling on the that given cubical block, then the amount of heat that is being absorbed, the Stefan's law is concerned for the radiation. So first we will be going for an amount of heat absorbed. So from the sun can be written as an solar constant into area into emissivity. So this is the amount of energy absorbed. So the rate of increase in the temperature will depend on the amount of energy or the power absorbed and the amount of energy radiated from that particular thing, or in the literally you can call it as an amount of energy present at the body. The rate of increase in the temperature will be decided. That's so rate of increase in temperature is equal to net power absorbed, that is the amount of the power that is falling on the object, and radiate minus radiating we should be good by thermal capacity, by thermal capacity. Or this you can get it like this, that is d capital T by d small t is equal to power by net power by, from this one this is MC. What do you mean by MC is nothing but an heat capacity or the thermal capacity. So this can be written as an solar constant into area into emissivity. This is the one which is falling on the substance, and this is the amount which is radiating from the substance. So the difference will give you the amount of energy contained with the substance. So now when I substitute the values here, solar constant is 1.4 kilowatts. So this is 1.4 into 10 to the power of 3 into area is been given as an 0.8 into 10 to the power of minus 2 here. Okay, now emissivity is 0.8 he has given minus. So this is the Stephen's constant. The value of the Stephen's constant is 5.67 into 10 to the power of minus 8. Next case in this one, into the area is going to be the 0.8 into 10 to the power of minus 2 into emissivity 0.8 into T power 4 in the sense, which is going to be the 300 to the power of 4 whole divided by. So mass is given as a 5 into 10 to the power of minus 4 into 0.8 into this is 4.2 into 10 to the power of 3 for the kilo conditions. Obviously on solving you might be getting it as in 3.6 Kelvin per second. So that should be your this particular thing. So next one please. A body of area, the same question, it's in paragraph question conditions. So the body of area is this much, every values are the same, emissivity and the specific heat is also same, surrounding temperature, maximum attainable temperature he is asking. So when the maximum attainable temperature, when at the maximum temperature, that is d capital T by d small t should be equal to the 0 for maximum temperature. So that means if I write the ms and everything, that is mass into specific heat, which implies that net power has to 0 at that particular instant. So what does it implies? Net power is equal to 0. That means the solar constant into area into emissivity minus sigma into emissivity E A T power 4. This entire thing has to be equal to the 0 for the total power conditions. So now, if you take common, or in this case, he is asking that particular T value is going to be how much. So from this, sigma E A T power 4 is equal to the solar constant into area into emissivity. So from this one, T power 4 can be written as an S by sigma. So from this one, you can write it as a temperature is going to be the solar constant by Stephen's constant to the power of this is 1 by 4. And that comes out to be the values of this one as 1.4 and yeah. So that will be the 1.4 into 10 to the power of 3 by. So Stephen's constant can be written as and this is 5.67 into 10 to the power of minus 8. So this value is going to be approximately it is 396 Kelvin. It comes out to be the case. So please try to understand this particular concept. When it's going to be the maximum, power is going to be the maximum conditions. Fine. So next case, question number 8. So a clock of metal pendulum of 15 degrees runs faster. 15 degrees is there. When it is at 15 degrees, it is running faster. That is 5 seconds each day. This is the important one. And 30 degrees, at 30 degrees, it is slow. So by 10 seconds, coefficient of linear expansion is answered. So that is the fractional change in the time period can be written as half alpha into delta t. This would be okay if it is not the day. Since it's a day, you need to write for the day also 86,400 seconds. So now if I go for the substitution of the values, it is 5 seconds is equal to, this is half alpha into change in temperature. I'm writing this one T minus 15. Here only I'm showing this slow or fast. I'm writing in the temperature itself into 86,400, and 10 seconds is equal to, it is half alpha into, it is 30 minus standard temperature where it can show you the correct value. This is the condition. So now when you solve these two things, so obviously all of them will be going off here. So this will be the 1 by 2. And this is 30 minus t is equal to 2t minus 30. Or from this one, 3t is equal to 60. Or t is equal to 20 degrees centigrade. It means at 20 degrees centigrade, it will show correct reading. Fine. So now substituting this value of the temperature in any one of the equations, that is 5 is equal to half alpha into change in temperature will be the 5 into this will be the 86,400 seconds. So now we can go for the solving of this one. Alpha can be written as n. It is 2 by 86,400, or it is 1 by 43200. So 1 by, if it have been 1 by 5 something else, or 1 by 500, the answer would be 2 into 10 to the power of something. So that means your answer should be just greater than the 2. So as for that one, I'm going 2.1 into, yes, given certain order, into 10 to the power of minus 5. Okay, so like this, it might be the there. I've just gone for an approximation here. Next one. The maximum in the energy distribution spectrum of the sun is at a wavelength of the 4,753 angstroms at this particular temperature. What will be the temperature of the star whose energy distribution shows this much wavelength? So this is the condition where Vane's displacement, Vane's displacement. So coming to the Vane's displacement law, that is the lambda maximum or maximum temperature or minimum wavelength is equal to temperature should be equal to the constant, or from this one lambda 1 T1 is equal to lambda 2 T2. So if I go for the sun here, so this will be the lambda value 4,753 angstroms into 6050 Kelvin is equal to lambda 2 9,506 angstroms into T2. So on solving T2, we should be getting it as an this is 4753 into 6050 by 9,506. So you should be getting approximately an amount of somewhere around 3,3025 Kelvin. Fine, sir. Next, coming to this one, in a container of negligible mass M, and a container is there, in the container mass is m grams, a negligible mass container, sorry, and m grams of the steam at 100 degrees is added to the 100 grams of water. So this much grams of the steam at 100 degrees is adding to the 100 grams of the water, which is at 20 degrees centigrade, it works on the principle of the calorimetry. If no heat is lost to the surroundings at equilibrium, then he is asking to match the things, please. Mass of the steam. If the mass of the steam is 20 grams, if I take it like this, if he is giving, then then he is asking what in the column 2. So match this one in the mass of the steam is equal to, if it is in this cases. So then he is asking how much mass is going to be left of the steam. Fine. Okay. So leftover steam he is asking. That's the thing, please. Okay, then if we go for this one, this is heat lost by the hot body is equal to heat gained by the cold body. So who is gaining the heat? Water. So that means mass of the water into specific heat of the water into rise in temperature of the water. So what is the mass of the water? 100 grams. Specific heat is 1. Rise in temperature from 20 degrees to 100 degrees, it might be. So if I go for this one, 100 grams into specific heat is 1 into this will be the 100 minus 20, that will be the 80. 80 into this one is going to be the 8,000 calories. So this, for this to happen, that means to have the 8,000 calories, how much steam is required? So heat is equal to, that is mass of the steam into latent heat, that is the conversion. So that means for this 8,000 calories, how much mass of the steam is necessary? Into this is 540. So which is equal to the mass of the steam is equal to 8,000 by 540, in the sense, though this will come out to be the 1, and leftover is going to be some 26, 260. 260 means it should be some 7, okay, 7, and this will be the some 8 grams. So let me take this one. So now given that if mass of the steam is 20 grams, then leftover mass of steam is 20 minus 17.8. Okay, so this should not be 17, this should be approximately 14 or the, yeah, sorry. This should be the 14 point something like this here. So if I go for this one, this should be the 14. So if I remove this one, approximately we'll be getting the 5.2 grams. So now if I go for this one, yeah. So that means this should be related to the C. So 1 has to be related to C. So next one, so if the mass of the, what is the mass of the water? If M is equal to 20 grams, same thing. So now he is asking the mass of the water. So that means mass of water should be equal to the, already there is 100 grams of the water plus this extra thing. What is the water that has been converted to this one? 14.8 grams. So this should be equal to the 114.84 grams. So this is second one is being related to the first one, that is 2 can be matched with A. So 1C2A, 1C2A, this is the only one option is there. You can go for this one. So let's conclude this one. Third option, if M is equal to 20 grams, final temperature. Obviously, it's going to be the final temperature will be 100 degrees only, because it is only sufficient to rise the temperature of the water from 20 degrees to the. So this is a final temperature will be, it should be the 100 degrees centigrade, sir. Next one, if the mass, suppose if the mass is going to be 10 grams, then he is asking what is an final temperature is going to be how much. So now to calculate that one, So we'll be going for an heat lost is equal to heat gain. So from this one, so heat lost by this one, suppose 10 grams into this is 540, which has been the latent heat, is equal to 100 grams of the water, specific heat 1, and it may not rise per 100 degrees. So this should be the 5400 is equal to 100 into this should be the T minus 20. Remove these two zeros. So T is equal to that is 54 plus 20. It should be the 74 Kelvin. We are going. I'm going for an approximation here. So this is the 70 roughly. This should be your answer. Okay. So now, so B should be your option.